Hess's law is great, but there's even a better way to figure out a delta H of a reaction if you know all the standard molar enthalpy of formation values. And so if you have any given reaction and you want to find its delta H of reaction, then what you can do is use this equation right here. And this is a little weird looking at first, so bear with me. This is the summation sign. It's a capital sigma, I believe, and that just means add up all of them. So you want to add up all of the heats of formation that are products and subtract from it the summation, add up all of the enthalpy of formations that are reactants. And I'll show you an example of how this means. So basically you want to add up the heats of formations of the products and subtract the heats of formations of the reactants. Now all the heats of formation are per 1 mole. So if your equation has, say, 2 moles of something, that's where N kicks in. So if you have 2 moles, you would use 2 for that. Or if you had 3 moles, you'd have 3, stuff like that. But in a nutshell, what this delta H calculation is showing is that it's all the energy that you gain minus the energy that you spend. And I'll show you this in a little bit more. So this is actually a pretty cool way to do things once you figure out how this all works. Let's say we want to find delta H reaction for this reaction, which is calcium carbonate breaking up into calcium oxide and carbon dioxide. So to figure this out, we're going to take the sum of all the heats of formation that are products, and we'll subtract from it the sum of all the heats of formation that are reactants. So for this problem, the products are calcium oxide and carbon dioxide, and the only reactant is calcium carbonate. So what we would do is in that table that's available at the end of problem set 3, or in that website I listed earlier, we would look up the delta HFs for calcium carbonate, calcium oxide, and carbon dioxide. So here's where you'd put those values. This would be the heat of formation for calcium oxide, a product, heat of formation for CO2, a product, and we'll subtract the heat of formation of our one product. Now, all of these stoichiometric coefficients in this reaction are 1, so we're not going to worry about those little n's right now because they're all just 1. Heats of formation are per mole, and we have just 1 mole, so it's no problem. So the next thing you do is you'd look up those values in the table of thermodynamics. So you can go to mhchem.org/thermo or look it up in problem set 3, whatever you want. But these are just numbers to look up. So calcium oxide apparently minus 635.1. Carbon dioxide minus 393.5, calcium carbonate minus 1206.2. Now, the only thing I sometimes see people getting confused is you want to make sure you go products minus reactants. So that's going to be essentially like adding 1206.2 kilojoules. But at the end of the day, then, this heat of reaction, positive 177.6 kilojoules. So for calcium carbonate to break down to calcium oxide and carbon dioxide, it's going to be endothermic. It's a positive delta H value. And that's kind of a cool thing to know. Now here's a reaction where methanol is being burned in oxygen to make CO2 and water, and we want to find the delta H reaction for this one. So this will be the same thing. It's going to be the products, CO2 and 2 waters, note the 2 right there, minus reactants, CH3OH and 3 halves O2. So like before, what we're going to do is we'll look the values up in that table of thermodynamic values for delta H. But there's 2 things I want to point out. Each of those delta H of formation values is per mole, and you can see you have 2 moles of water here. So whatever delta HF for gaseous water is, you want to multiply it by 2 because there's a 2 in the reaction. Now the other thing is that we have 3 halves O2, and if O2 had a value, you'd multiply it by 3 too. However, oxygen is an element in its standard state, and all the delta HF values for the elements in their standard state are 0. You can look it up if you don't believe me, but honestly it is. So in this case then, it helps to know that the water you'll multiply by 2. It helps to know that the O2 is a reactant in its standard state, so it's going to have a delta HF value of 0. So in this problem then, when you look up those values, here's the equation written out. And again, notice that there's a 2 there by the delta HF because we have 2 moles of water in the reaction. So if you don't have just ones, that's when you use the 2s. That would be the N value, if you will, for the value in front of delta HF for water. So again, just plug and chug. There's CO2. We saw that earlier. No big deal. Here's water, but we're going to multiply it by 2. That's because in the balanced reaction, there's a 2 right there. From that, we'll subtract the reactants. Oxygen is 0. The CH3OH would be minus 201.5. So at the end of the day, your delta H value, minus 675.6 kilojoules per mole. Good to go. So burning alcohol, like methanol here, usually exothermic. It's going to have a negative number. Here's the kind of question you might see. I'd like you to find the delta H of reaction for this reaction, C2H2 plus hydrogen making C2H4. C2H2 is acetylene, C2H4 is ethene. So we're making, or ethylene as it sometimes is called. So you're basically turning acetylene into ethylene, but don't worry about that. Now, I've only given you 2 of the 3 chemical delta HF values right there. And remember, delta H will be products minus reactants. So we've got C2H4, that's the positive 52.5. And from the product, I want to subtract all the reactants. So I've got C2H2, that'll be minus 226.7, but I don't have hydrogen, all right? Hydrogen, however, is an element in its standard state. So like O2 gas, like Na solid, like xenon is a gas, et cetera, all of those are going to have delta HF values of 0. So if there isn't a value given, then that usually means it's just 0, to be totally honest. So anyway, at 52.5 minus reactants, in this case minus 226.7, gets you negative 174.2 kilojoules per mole of reaction. So that's just kind of how this works out. Usually if the delta HF isn't given, then usually it's 0, but you should check with a table to make sure, stuff like that.